All right, we're going to take a look at another type of differential equation. This one we're going to classify as a first-order linear differential equation. Now, if it is a first-order linear differential equation, it can always be written in this form: y prime plus p of x y is equal to some function of x. So this is the generic form for a first-order, highest order is 1, linear, because all the y's are the first power not multiplied together, differential equation. If it has this form, then there's a very specific method that you can solve these. You might be able to separate it like we've seen in the past, depending on what f of x is and how things are. Most of the time, though, you're going to try this method. Now, this is a pretty interesting technique here. Somebody decided this idea. This side almost looks like the product rule, because we have two things added together, and we have y prime and then just a y. Kind of looks like that, but it's really not using the product rule. But they said, could I multiply through by a function, some random function, and turn this side into a product rule, which I could write as a derivative? Here's what I mean. Let's say we're going to use something called an integrating factor. Now, an integrating factor is anything that helps you integrate something that was difficult. Our integrating factor, we're going to say, is some function of x. Now, most of the time we use the Greek letter mu here, and that's what I'm going to do. The idea here is I'm going to multiply through this equation by some function of x. And I want to turn this side here into the derivative of mu times something, or I'm sorry, y times whatever that mu is. I want the left-hand side to turn into y times the derivative of whatever this function is. If that's true, then if I integrate that, if you integrate the derivative, it goes away. So it makes the left-hand side very, very easy to deal with. The trick is, how do we figure out what this function has to be to turn this side into a derivative of something else? Well, to do that, we're going to multiply through by that, whatever this function is. So on the left-hand side, I'm going to drop the function notation. So that's mu y prime plus mu p of xy is equal to mu f of x. All right, now I'm going to start just by looking at this piece right here. Because remember, I want this to be the derivative of something. So I want that to end up being the derivative of mu, messed up with mu times y. All right, so mu times y. So what would the derivative of that actually be? Well, that'd be mu prime y plus mu, come on, y. But what do we actually have over there right now? We have this piece, so we want that to be equal to mu y prime plus mu p of x y. So we want this to be the derivative of mu y. So what would it take for these two things to be equal to each other? There's a prime right there. So as you can see, this piece and this piece are the same on both sides, so those would cancel, which means that mu prime y has to be the same as mu p of xy. All right, now I'm going to divide both sides by y, but you always want to be really careful anytime you divide by a variable. How do I know y is not 0? Well, if y was 0, that means this whole side over here would be 0 and not equal to some function of x, unless that function of x was exactly 0. So it's pretty safe to say that y is most likely not 0. So if I divide that out, I get mu prime is equal to mu times p of x. Well, what this is this is a first order it's linear still, first order linear differential equation. But this is now separable, or this is separable. Remember, this is the derivative with respect to x. Is equal to mu p of x. And we can separate our variables. So d mu is equal to mu p of x dx. And if I move all my mu's to one side, d mu over mu is equal to p of x dx. Now if we integrate both sides, is equal to the integral of p of x dx. Well, on the left-hand side, this ends up being the natural log of the absolute value of mu is equal to, well, I don't know what that is, because I don't know what the function p of x is, right? P of x is some arbitrary function that's going to end up here, so I can't do that integral yet. But I can solve for mu. I can write this as e to the integral of p of x dx. Now that's the absolute value of mu, which means you get a plus or minus here for mu. You would get that mu is equal to plus or minus e to the integral of p of x dx. However, remember what we're going to do with the mu. We're going to multiply through the entire equation by mu. So it doesn't matter if it's positive or negative, so just pick the positive. So generally speaking, we're just going to say our integrating factor is always going to be e to the integral of p of x dx. All right, now the good news is you don't ever have to do that again. I did it for you. I told you what the integrating factor is. So how does this work out now? Well, let's start with a very simple one and see how it works. So by the way, I'm going to put this over here. This is our which I generally am going to abbreviate IF. Okay, so let's say that I have a differential equation that looks like this. Y prime plus 3y is equal to 4. All right, so to classify this, well, the first thing we try to do is try to separate it. You wouldn't be able to separate this, by the way. This is a first-order linear differential equation. So in the back of your head, you're thinking, okay, I'm going to use an integrating factor for this. So what would our integrating factor be? Well, the integrating factor is e to the integral of whatever p of x is. And by definition, once you have the derivative alone and out front, p of x is whatever's in front of the y. So this is just 3 dx. So our integrating factor is e to the 3x. All right, now here's the good news. We don't have to go through a ton of work, right? Because we know once we multiply the left-hand side by that, it's just the derivative of the integrating factor times the dependent variable. So I'm going to write this step for this first one, and I'm never going to write it again. This is e to the 3x, y, plus 3e to the 3x, y is equal to 4 times e to the 3x. Now check it for yourself. This here ends up being the derivative of the integrating factor times the dependent variable. And that's the way you want to remember it. Always, the left-hand side always turns into the integrating factor times the dependent variable. Now on the right-hand side, that's just 4e to the 3x. Now we need to integrate both sides. So if I integrate both sides here, let's write it like this. Remember, this is the derivative with respect to x. Let me take one more step so you can see it. So if we're going to separate our variables, kind of like we did last time, this would be 4e to the 3x dx, and e to the 3xy is equal to the integral of 4e to the 3x dx. Okay, each one of those integrals should be easy because the left-hand side, again, always ends up being the same. So I'm showing a lot of work here that I'm going to start skipping because I know that this always works out the same way. That's why we did all that work to find that integrating factor. On the left-hand side, once we multiply through right as the derivative and integrate, you get the integrating factor times the dependent variable. On the right-hand side, we still have to integrate that. Well, integrating that is going to give me 4/3 e to the 3x plus c. All right, so to finish solving for this one would be easy to solve for y. So if I divide through by e to the 3x, again, that's never 0, so I can divide through by it. That's 4/3 plus c e to the negative 3x. And there's our solution. All right, so first order linear. Once you decide it is first order linear, you're going to use an integrating factor. You multiply through the entire equation by the integrating factor. The left-hand side always becomes the integrating factor times the dependent variable. On the right-hand side is where all your work's going to end up happening. You're going to have to multiply and integrate, and the integration's not always particularly easy. All right, let's take a look at another example or two. Let's say if I show about x squared y prime plus 2xy is equal to 1. All right, now this doesn't quite fit our form. Remember, our form looks like this: y prime plus p of x y is equal to some function over there. Doesn't quite fit our form. So if you're looking for this, you always want the derivative to be out there in front by itself. So I'm going to divide through by x squared. Now I just said you got to be careful if you divide through by a variable. And that's true, but if x is 0, that means that everything is 0. We get what? 0 equals 1. Well, 0 doesn't equal 1, so I know that x can't be 0 and be a solution to this equation. So if I divide through by x squared, I get y prime plus 2 over xy is equal to, that's not right, 1 over x squared. Okay, so we can now see that this fits this form exactly. Y prime plus some function of xy is equal to just some function of x. So we know to solve this type of problem, we're going to use an integrating factor. Our integrating factor is always e to the integral of whatever's in front of the y, which is our p of x dx. This is 2 over x dx. So this is e 2 times the integral of 1 over x dx. So this is 2 times the natural log of the absolute value of x, which we can bring up that 2 there using our properties of log. And the nice thing, I can get rid of that absolute value in this one because I know if I square something, it's always positive. So this just ends up being x squared. All right, so remember what's going to happen on the left-hand side. We multiply through the entire equation by x squared. On the left-hand side, you're always going to end up, once you multiply through and integrate, is the integrating factor times the dependent variable. On the right-hand side, you need to take that function, multiply it by the integrating factor, and integrate. So we get x squared y is equal to the integral of dx. So x squared y is equal to 1, ridiculous, x plus some integrating constant. Again, easy to solve for y. Again, we're dividing through by x, but we've already decided that's not 0, so we can do that. Okay, so there is our solution. Now, like always, if you want to make sure that something is a solution, all you got to do is what? Take all the derivatives, plug it in here, and see if it checks out. All right, let's try one more. Let's go back over this way, maybe one that's a little bit more complicated. What if I said, cosine xy prime plus sine xy is equal to sine x cosine x. Really scary looking. All right, so let's take a look. All right, to do this, what are we going to do? Well, we want to get our derivative alone all by itself, so let's divide through by cosine. Now, in this case, could cosine be 0? Cosine of 0. Well, if cosine 0, that means this would be 0 and 0. Well, sine's not 0 at the same place cosine's 0 at, so that means that would not be a solution, so we should be able to divide through by. So that would be sine x over cosine x, y is equal to just the sine of x. All right, this is a first order linear differential equation, so we're going to try using an integrating factor. So what would our integrating factor be? Well, it would be e to the integral of, well, that's tangent if you wanted to write it as tangent, but cosine x over sine x. The integral of cosine x over sine x is negative natural log absolute value of cosine. Now again, I can put up that negative there, so this is e natural log of cosine x to the negative 1, which is the secant. Okay, now to get this will go away, but we end up with the absolute value here. And I really don't want this absolute value it's going to make the integration up here difficult. So a lot of times, what we're going to do is make sure that this is always positive. So where is secant positive? Well, that's where cosine is positive. So the easiest way to say this is cosine is what all students take calculus, right? So in the first and fourth quadrants. So if we just say, let's let x fall between negative pi over 2 and pi over 2, that'll make sure that this is positive, and then I can just use the secant of x. All right, so what are we going to end up with on the left-hand side? Well, on the left-hand side, you always get the integrating factor times the dependent variable. On the right-hand side, you're going to have to multiply and integrate. I get the secant y is equal to, well, to write this, it would probably be easier to write this as the sine x over the cosine of x, which we just did a second ago. That's the negative natural log of the absolute value of cosine, plus c. All right, so to solve for y, all we got to do is multiply through by cosine, or divide through by secant, same thing. So we get y is equal to negative cosine x times the natural log absolute value of cosine x plus c times cosine of x. All right, so there we go. There is our solution. Now, not quite, because remember, this is also part of our solution, because we made that assumption to make our work a little bit easier. If we hadn't done that, we would have had an integral right here that had an absolute value in it, where you would end up having to do something like this anyway, or something close to that. All right, so first order linear differential equations, as long as it fits the form, basically always divide through by your lead coefficient. If you have y prime plus some function of x, y is equal to some function of x, it's first order linear. You can use an integrating factor to help you integrate it. It's e to the integral of whatever p of x is dx. Once you multiply both sides by that integrating factor and integrate, on the left-hand side, you always get the integrating factor times the dependent variable. On the right-hand side, that's where all your work's going to come into play. You need to integrate the right-hand side, and then on these, you can actually solve for y, so it's not too bad. So make sure that you're giving these a shot.